Hi. So today I have a very interesting thing to discuss. I was collecting these seashells on the seashore, and what I observed was there is a very interesting pattern that these kind of seashells exhibit. So you can see a spiral pattern here, as if in all these, as if the creature that was starting out from here kind of increased the radius of its habitat by a constant amount. And there seems to be a pattern in these seashells, as in the radius is constantly increasing following some pattern. So I thought if we can mathematically model this and come up with a way as to how these seashells form and what exactly is the growth pattern that they follow, can we deduce that mathematically? So let's see what interesting things we can do. So let's say that these growth patterns exhibit a very the simplest build up that you can think of. So for example, it grows as a constant build up. For example, s of n plus s of n, for example, is found by Sn minus 1 plus Sn minus 2. That's the most simplest recursive build up that you can think of, right? That size at any given moment is just a build up from previous sizes, correct? And also it's a constant growth, right? So if we have, for example, starting out with a size s naught, then it grows to, say, the growth factor is f, so f times s naught and f square times s naught, so as in a geometric progression. So if we just plug that in here, so say for example we do it for the first couple of sequences. So the very first number here is s naught, and that builds up by a factor of f times s naught to create f square times f naught. So basically the relationship that we have is f square equals f plus 1. And this is a very simple quadratic relationship that we can solve to obtain f equals plus 1 plus root 5 by 2. And of course, since this fraction has to be positive, the only valid natural solution is this. Now this number 1 plus root 5 by 2 in decimal terms, which is 1.618, is a very interesting number which is called the golden ratio phi. So this golden ratio phi is found in nature very commonly, as in you can see the radius of these shells grow with this kind of a factor of f. And the reason for that is very simple, because if the growth factor is a constant, and the recursive relationship that they use for growth has to be the simplest possible, because you think it makes sense in an evolutionary kind of perspective, because if you're a creature, evolutionary sense dictates that you have to conserve energy and resources. So the simplest relationship that you can follow is a recursive relationship that simply builds onto the previous, right? So that's why this golden ratio phi is very ubiquitous in whole of nature. It's a very powerful thing, as in if you draw a square that has its aspect ratio in this golden ratio phi, then that is very aesthetically pleasing. So it's used in all forms of architecture, art. Leonardo da Vinci has used it in creating Mona Lisa, it is said. And all kind of ancient Greek and Roman monuments, they have used this ratio time and again. So what is interesting is that so it's basically kind of a build-up in which the sequence is also additive and multiplicative. For example, in going from the sequence A1, A2, A3, each additional term is growing by a constant factor of f naught, which is phi, and also each term is a sum of previous two terms. So it's basically a balance between addition and multiplication. So a simple sequence that follows this is a Fibonacci sequence, as we all know. So basically 1, 1, 2, 3, 5, 8, every term is a sequence, is a addition of the previous two terms, right? And interestingly, if you see, if you approximate this, so if you do 1 divided by 1, then 2 divided by 1, and then 5 divided by 3, 8 divided by 5, what you'll observe is that this Fibonacci sequence actually these ratios approach 1.618. So for example, if you take a very big number, so 55 is one of a Fibonacci numbers, and I ask you which is the next, what is the next number going to be. So if you just multiply this by 1.618, right, you'll get the next number, which is 89 approximately. So basically Fibonacci sequence and this golden ratio are also very closely connected because they also follow a similar mechanism. So that was a quick discussion about the golden ratio, how it occurs in nature, why it is so ubiquitous, and how is it related to mathematics. So math is beautiful and relates so beautifully and elegantly to the nature around us. That's why I love it.